time that I had Google, Microsoft, and Amazon.
Yeah.
So Google hasn't responded to like my times for my phone screen. And then Amazon, I don't know what's going on with them internally, but my recruiter was like, yo, your scheduled interviews are gonna have to be canceled. And then he just left it there. Like
Interesting.
he's trying to look, yeah, he's trying to look for someone for me.
Mm.
Um, and then Microsoft, I passed the phone screen like literally 2 days after I interviewed with you.
Yeah.
And so I'm now into on the 19th, I have my final rounds with Microsoft.
Nice.
And then just yesterday or 2 days ago, a Meta recruiter reached out to
No
me.
way.
Yeah,
That's
so I have a
good.
phone. Yeah, I have a phone screen with Meta now on the 26th. So
That's
there you
crazy.
go.
Literally got everything in the acronym now.
Yeah, bro, I
Most
got.
things.
Well, I don't have Apple and Netflix though, but
Yeah.
you know, that's still a good amount of the Infinity Stones.
Yeah.
So,
How are you feeling? What advice did I give you last time?
bro, I'm so nervous. Let me. What? I think. Well, I think the main issue that I had was the first one was because the Atlantic and Pacific, I knew it, um, and you told me to like pretend that you don't know it, pretty much. And then
Or
and
I
then
think I
also
think my advice was when you explain it
yeah, yeah,
in
yeah,
in
yeah,
a
yeah, yeah,
way that's
yeah.
doesn't sound
Yep.
like you're just regurgitating the solution.
Yeah, yeah, yeah. And then and we also and then you gave me advice to like learn more about the like Python string, like standard string methods and functions. Because I hated them or I hate like working with strings. And so like I had trouble remembering what those actually do or how they work.
Mm-hmm.
So I think that was the your advice for the first one. Um, yeah.
Cool.
So that's where we left off pretty much.
All right. Okay. You're in this chat. Let's just get straight into this next part then.
Sure,
So
sure, sure.
we're in this one. We're gonna be designing. There's gonna be multiple parts to this question. Do you like to use Python for your
Yeah,
interviews?
yeah, yeah. Python's good.
All right.
And I hate these multiple like phases as well.
This one, we're
Oh,
just gonna be implementing a simple data structure. We're gonna be designing a graph. So implement it with these following. Implement the graph with these following methods
oh
for now.
no. Okay. Let me see. Okay, okay. Uh, Directed graph. Okay. So we have edges, add edge.
Yeah.
Okay. So uh, to design a graph, technically, what we're kind of asking here is to also design the nodes themselves. Is it okay if I just start off with like a basic node implementation, just
So
so that
how
I
how,
can?
how are you thinking of so we're gonna be creating this directed graph, right?
Yep.
So
Yeah.
what's the underlying data structure, or
Uh, I think so. We're you're. This is kind of like asking for like an adjacency list. So I think we can start off with using a dictionary to store specifically the nodes and then neighbors as well. Does that make sense?
sure? So we're gonna have a dictionary to represent this graph.
Yes, I think that's how.
Sure. I mean, there's multiple
Mm,
ways we can represent it, so I just want you to choose one, and
okay.
maybe we might need to
Yeah.
change it, but not sure yet.
Um, okay. Oh, let me think about this more then. Um, so really, I think my biggest concern right now is how do I represent the edges here? But so the node itself, oh, the node is an int. So yeah, I think I'm comfortable with starting it with a dictionary if we're doing int here or ints for nodes, not like an actual like node class. Um, yeah. So are you good with me starting on that?
So you're gonna use a hash map?
Yeah, pretty
Okay.
much.
Yeah, I'm fine. I'm just curious. What are the other ways that we could store this graph, represent this graph?
Uh, I'm blanking out here. No clue.
Hmm.
Uh,
Okay, that's fine. Let's just go with the hash map.
Sure. Okay. Let me just. Hmm. Sorry. Init, and then we're not inserting anything into the graph class itself, right?
Into the graph class.
Like
Uh,
like we're not like we don't have anything for like. Never mind. Never mind. I'm overthinking it, I think.
yeah.
Uh, okay. Um, like I think neighbors here, right? You can do, and then let me just initialize everything else first. Self node add edge uh, from int to int and as edge int to int pass. Oop. Let's not forget the self here. Um, okay, yeah. And then so I think to add like for here, so if we add a node, we can check first if the node is not already in the neighbors. So if node in self neighbors, right? And then self neighbors node. We can actually set it as a set because we don't care. We won't have any. Are we going to have duplicates here or like are we going to have nodes that have like the same uh
Like the same edge multiple times? Would
yeah,
we want that? Can we in our
no, yeah, no, I don't think so. Okay, and then for add edge, right, we have to add edge. And directed edge from to. Yeah. First, we have to actually check if they both exist in the neighbors. So if from in self neighbors and to uh, in self neighbors, we oh is that a let's change it then source destination. Let's go. let's do that. If destination, source, let's do that. Let's change it here. Then we can sell out neighbors. Source.
We could assume that we added the nodes before we ever add an edge.
Okay, so okay, in that case, then we don't necessarily need this then, right?
Sure.
And then we can just add destination. Directed edge. Yep. And then also for this one has edge in check. So in check if source is not inside the self.neighbors. Then we'll return false, right?
Has edge source not in self.neighbors. Okay.
Yeah, just because like it's just checking, like if the node that we're the edge is going towards.
Okay, I see. Yeah, makes sense.
Yeah. Okay. And then otherwise, right? Destination. Oh, neighbors.
Otherwise, return destination is in the neighbors. We just
Yep.
need to return a bool here, right? Like, is it if the edge exists?
Yeah. In this case, it would, right? Because we have to check. Like first, we're checking if the source itself is in the neighbors, or technically the adjacency list, right? If it is, because we're storing the source or the neighbors, or sorry, the source. Sorry, if we are storing the destination inside the node or the source, right? Like in this dictionary, then we know there's an edge in there.
This makes sense. Could you go ahead and write some code to test it?
Yeah. Graph equals graph. Okay. And then so let's add node. Let's see. Let's do 5, right? Let's run that first. Cool. So, and then let's do an edge case here and just check for something random, right? Like 5, and then 8. Let's print that 2. Right. Okay, cool, false. And then so let's then add an add edge. Which 5. Let's do, actually. Oh, sorry. We're assuming, so for add edge, we're assuming that both the source and destination already exist, right?
Yep.
Okay, so then let's do that. So this should then
has an edge from 5 to 8.
Yeah, this actually still will return false, but if we do it again, because we don't necessarily have the edge set up already, if we do it again, it should return true. Yep.
Nice.
So
what about the other way around? If we go 8 to 5.
Graph has edge 8 to 5. Oh. Doesn't.
Is it supposed to?
No, because it's directed.
Yep.
Yeah. So in that case, yeah, it shouldn't. So this makes sense.
Okay. Sounds good. So I want you to implement me a like a DFS and a BFS here.
Oh. Okay. specifically, what would they be looking for? Pretty much like cycle or what?
I just want you to just write me some code that performs a DFS from any node, any starting node.
Any starting node.
Yeah.
Okay.
So if we call DFS, yeah, with some starting node, it'll perform a depth first search from that node and return me a
Hmm.
list of all the nodes it traversed in the order that it traversed them.
A starting node, and then also a destination node, or just a node?
Just a node.
Oh, okay.
Was
We're
it?
gonna
Would
have
it matter if we did this?
okay.
Or I'm wondering, does this question like why would it matter if we know this or the destination?
Oh no, no, okay, I get you because it's directed edge. Like we're just gonna go through. Okay, that makes sense. Sorry, sorry. Okay. Um, let's do. We can do the perform DFS and actually have a DFS in there, possibly. I think because like that way we can just do like the path here, uh, right? Um, let's do this, and then we can return the path right here. Um, and so uh, for the DFS, we can do a curve.
But let's see. I don't want you to break the API.
Oh,
As
okay.
in, if let's write the functions like this. From a from an API perspective, I don't like the name perform DFS. Like
Okay,
somebody having
okay.
to call that.
Okay, sure. Let me just do this then. Um, BFS start int, and then I'll pass this for now, and then we can do with BFS. I prefer that much more than um, BFS. Okay, so let's just invert it. How about that? And then for path. Am I doing this right? What do you think? Uh, let's just do it here. If okay, so we are looping through DFS, and we're going to start. Let me do like some drawing here. So let's say our dictionary currently is kind of like, you know, five, five. Let's do.
We're gonna do BFS first.
No, no, no. I'm doing DFS
Okay, I
first.
see. I see.
But I just want to do like a visualization here, just so that I can actually kind of understand how we're doing this. So 6, and then 8, right? So, and then 8. Yeah, okay. In this case, right? So let's say the FS start would be like 5, right? So we go into currently, obviously, we'll have 5 up in there, right, in the path. And then it's going to go into 6 first. Oh, we don't have 6. Let's do like 4. Okay. Okay. So go into 6, do a DFS on 6, right? And then it will go to 4. And so in that case, we'll have 5 and 6, and then it will DFS into 4, which in this case, it would be 5, 6, 4, 5, 6, 4. right? And then it will actually stop there for 5 or for 6. And then DFS will go into 7 again because we started with 5. In which case, it'll go into 6 again. But I think in this case, we would check. So we would have to check if the node is already in our current path. In which
Wait, so
case, go ahead.
question, like how do you how do you usually perform a DFS? Like, what are the different ways to perform a DFS?
You can do an iterative or a recursive DFS. Really, I mean, they're pretty much one and the same, right? The iterative just uses a stack, while the recursive uses recursion, or AKA a call stack, right, of the function itself. So
Okay, so how would you pretend we want to do it with a stack, or recursively, or iteratively with a stack? How would you do that?
that's a good question. I don't normally practice DFS with the iterative. But it kind of mirrors BFS, right? I think, because if you have a stack, right, let's pretend the path itself here is the stack itself. We don't necessarily need like a recursive function anymore. In this case, it would just be while stack, right? And then you perform all of your whatever needs to be done within the recursive function within that while stack loop. Does that make sense?
Mm-hmm.
Am I? Did I get there?
Okay, yeah. I think
You want me to?
no need to visualize it. Just go ahead and
Sure.
implement it.
Yeah. Okay. Sorry. I was implementing it, or I was visualizing it because I was kind of confused.
Okay.
So you want me to do it with the iterative way,
Yep.
or
Yep.
okay? Let's do then while stack. Okay. Per equals stack pop, right? Stack pop. So in this case, we have to put in the start in there. Yeah, obviously we would have to, otherwise this wouldn't loop through, right? So we check. So then we check if cur is already in path, in which case you just continue, I think, right? Because we don't want to, that's kind of like an endless loop, so to speak. Okay. And then we do a path. Otherwise, we continue, and then
In
we
path.
have to add all of their the nodes that they have an edge towards. So in that case, for how do I do this? For and south on, what did I call it again? Neighbors. Per it's a set. Wait. So there we go. Okay. For node in stack.append node. And then in that case, we just path.append per. So that feels deceptively. I don't know if I'm doing that the right way. like I said, I rarely implement DFS in the iterative way. Um, so, uh, oh,
Can you
yep.
walk me through line by line? What's going on here?
Yeah. Okay. So we first initialize the stack with the start, right? In this case, and then empty. Obviously, a path is empty. So when we get through the while stack, we pop. So in this case, this would be 5, right? And then we have to check if, well, actually, I never asked. Do we want to go through the all the cycles again? Like, because that's kind of what I was visualizing here, right? Because eventually we get to 7, right? And we hit the 6. Oh, we do actually. So you don't need this.
We want to view the cycle? Well, we just want to perform a DFS, so print out all of the nodes, but traverse them in
Okay.
a DFS order. If we go through cycles, we're going to end up in an infinite loop.
Right. Yeah, let me just yeah
Okay, sure.
yeah let me yeah. So like I said, so our cur right here is 5. Um, let me just implement it this way and see if there's some issue with the logic itself. But 5 isn't in our path, so we go in and we check in a dictionary um, all the directed edges that it has.
Sure.
So in this case, it would be 6 and 7. So we append that into the stack, and then we append cur into the path. And then, so we go loop through that again. In this case, it would be 6, right? 6 is in our path. And then we also then go into the neighbors or edges technically. And then we see that 4 is an edge. So we append that. So in that case, our stack currently is 7 and 4.
Mm-hmm.
And then we append 6 here. So our path is 5, 4 or 5, 6. And then we pop it again. It's 7. 7 is not our path. 4 node.
Yep.
And then yeah, we check it again. So 6 and 8 is in our
Okay.
path, right? Or in our stack.
Yep.
So,
What's the time and space, or what's the time complexity of this DFS?
uh, this would be um, it would be m times n, where m is the size of the neighbors of the dictionary itself, and then n, or did I say m? Whatever. So it's m, which is the size of the dictionary itself, and
Mm.
then n is the size of technically it would be the size of, I think, the max uh, um, a max of like the edges. Whoever
Okay.
has the most
Let's
edges.
see. I think your DFS operation might actually take even longer than that.
Oh, really? Okay.
Like there's this O of N operation happening here,
Oh,
right? Like
okay.
every time you're trying to see if it's already been in the path, you're running another O of N. So it's
Yeah. Okay, so yeah,
when it
that
comes
makes
to,
sense.
yeah.
Okay.
So it's kind of like N squared, or N
Right.
N squared times M.
Right. Oh, it's an interesting one. Um, do you want me to move over to BFS? Actually, so in that case, then would would having a visited um a set in there, like we can just add the cur or like visited dot add cur again in there, and we just check if it's been visited. All right. Is that
If current node invisited, continue. Okay.
yeah? Or actually, we can also flip this and check. We can check it in here. I just realized that. Right. If node invisited, we can stack. In that case, like we don't care about the node anymore. Does that make sense?
Yep.
Yeah. So, um, I think that optimizes it. Does it not?
Okay. Go ahead with the BFS now.
Sure. Okay. So BFS, kind of like the iterative, it has a queue, which we will initiate as double-ended queue. Let me just import that. Collections import. Okay. And actually, yeah. Sorry, I forgot to ask. Like the start parameter. This is guaranteed to actually be in
Yep.
the
Yeah.
dictionary, right?
Yes.
Um, okay. And then we have a visited, which will be start. We can have start in there. Actually, also want start in here. All right. And then we have path here, and then we return path. And then while q, right, cur equals q dot pop left, and then we can just append the path right here, or append cur right here. And then for neighbor, or edge, technically for edge and self neighbors. I don't know why I named it neighbors. Yeah, it's a dictionary. So, oh, did I mess up on that one? I think it's dot get right here. Um, yeah. Oh, oh, think curve. Is it like that? Yeah. Neighbors. Okay. Get cur, and then this. Let's add self in there. For edge. And then what do we do? Oh, we add it into, we also check if edge and visited, not in visited, right? Visited, not add edge. And then you set here, right? Yeah. There we go. Visited, add edge, and then q dot append edge, and then we return path. I believe that's the BFS there.
Add. Okay. All right. Let's move on to the very last part. I think I'm okay with it for now.
Okay.
So I want you to do the following.
Mm-hmm.
I'll write it at the bottom, or I'll write it above. Or I'll write it above here. So we update the add edge to support adding a weight, and then write me a function that returns the shortest path between a source and a target.
Oh no. Okay. I'm cooked. Now, how do I do this with my data structure? Let's see. I knew this is where you were going with it, with the
You're
weight.
thinking?
Yeah. Uh, that's not very future thinking of me. Because at this point, I mean, we can change it so that it's like a tuple,
Yeah, like does
right?
much really need to change? I know.
Uh, I think so. Because I'm trying to think here how we would add in the weight, right? Well, actually, yeah. We can add a tuple. So rather than in the add edges, so it's no longer um yeah. It's no longer uh just the edge itself, but it's the edge slash weight in this case. So um oops. Yeah. So in this case, our self at neighbors dictionary uh, within the set itself for each node, it's going to be a tuple of the destination and the weight. Does that make sense?
Sure. Yeah. Makes
Um,
sense.
in this case, so then add edge is weight int. In this case, then as well, we can do weight, right? Let's see. Set if add node has edge. I think this one do matter.
I mean that looks fine for adding the weight.
Okay.
How
And
would you
then
get the shortest path between a source and a destination?
yeah, let's shortest path. I think this is well, this would be I think a DFS, right? Or at least I think it would be.
How would it work?
Um, it would be. Oh God, this is it Dijkstra's, which I'll be very completely upfront with you. I don't know how to implement right now. I know I think it uses a heap, right?
Mm-hmm.
But that's all I know about it.
Yeah.
Um, so I'm kind of cooked on this one. Um, so this is yeah, source int target int. Um, let's just return whatever for now. Because how does the
Are you familiar with Dijkstra's? You've ever had to do it in school or remember?
yeah, I school was like years ago, 4 years ago.
Yeah.
But yeah, I came across it. Like generally, like the problems that I've come across, you can implement like um, Dijkstra's, but also for those problems, I remember being able to also implement it the DFS way.
Yeah.
Um, but I think in this case, can you implement it without using Dijkstra's?
Yeah. Not really. Well, if you want to calculate the shortest path, there's
Yeah,
only a
yeah,
few shortest path algorithms that are
yeah.
optimal.
Mhm. Yeah. I mean, all I know is right. You do like a heap.
Yeah.
Um, and I think it's like
Yeah.
uh
It's fine though. We've already it's already we're already
yeah
40 minutes in. So
yeah.
all right, how do you think you did? How was that for you?
This was a fun one to be honest with you.
Yeah.
Breath first search and net first search is pretty good. Seems like I definitely need to hammer down on Dijkstra's. Yeah, I think yeah. Overall, I think I like this was pretty good.
Yeah.
So.
Okay, let's look at it. I think so for
Mhm,
part one you pretty much sped through it. You're able to do it fast. Implementation made sense. So there's
mhm.
different ways to store the adjacency list. You could use a hash map. Another way is using adjacency matrix. So
Oh yeah, yeah, yeah.
but these no it doesn't really work for this one because these nodes are it's the matrix is gonna be really sparse. But sometimes if the matrix is dense,
Mhm.
using an adjacency matrix is option. But those are just two different ones. I just wanted to see if you could like if you knew.
Gotcha.
But
Yeah, I thought you were talking about something else. I definitely knew about like the adjacency matrix, but generally, like for the most part, I prefer the dictionary.
yeah, and then
So,
I think for the second one, second question
mhm.
I think just be able to implement DFS both iteratively and recursively, and be able
uh,
to do it fast. So I think it took a while and you were getting tripped up with the implementation. I think it could be
mhm.
cleaned up a little bit. Let's see. So one way you could let's see DFS. So in the DFS, let's walk through it. You start at the start,
Yep.
and then you
Oh, I
have the
forgot.
yeah. I think it looks good eventually, but
Uh-huh.
one way you could also just add to visited here. Start.
Yeah. Just saw that right now.
What else? Path. Dot append. Yeah, it took a bit to optimize it. You started off with unoptimal, but we're slowly able to
Mhm.
iterate it.
Yep.
But which is not bad. It showed that you had good problem solving skills. Was genuinely the first time you did it and you were able to solve it. But I think for
Mhm.
most interviews, because they won't ask you just straight up DFS, it's always going to be a twist to it. You should be
Uh-huh.
able to pump out a regular DFS pretty fast, and then the iterative or the other version, like the variant that you have to do, it'll make it a
Cool.
lot easier. Because if it's the first time you're implementing iterative DFS in the interview, you might trip up.
Mhm.
Let's see. Current pop for node in neighbors. If the node is visited, continue. Okay, this makes sense now. And then one other way is would just be, one way that I would just change this up would be something like this.
Oh, you do it at the start? Okay, that makes
Like
sense.
while we're visiting it, we're visiting that current node,
Right.
and then if the node isn't visited, we continue.
Mhm.
Otherwise, we just add it to the stack and then we visit it right away, kind of thing.
Gotcha.
Because pretend I have multiple because I want to everything needs to go into the stack exactly once, so I only iterate
Mhm.
over it once. If
Yep.
you add it to visited later, sometimes you could add the same element to stack a bunch of times, and it just in some questions it will lead you to a it will just the runtime is just slower, and it could
Mhm.
actually ruin your runtime on some questions and get a TLE.
Gotcha. Gotcha.
Yeah,
Cool.
and then you implement the BFS pretty fast, but pretend we're doing this interview, I had to do it really fast. It's pretty much
Uh-huh.
almost just a copy and paste too. You could just copy the BFS right here, and just change a couple things, change the queue.
Oh,
But
yeah,
but
I
I think it's fine to implement it from scratch. But yeah, this chat
right.
was just saying that. Let's see,
Uh-huh.
and then even your DFS and BFS, you didn't implement them consistently, as in they're
Uh-huh.
slightly different.
Gotcha.
So
Okay.
they
Yeah,
should be pretty much. You should be
the
able to
same.
pretty much the same except for one's using the queue. So
Gotcha.
even with the way
Okay.
you did the visited, so that's
Yeah.
yeah. So that's not really anything wrong. It's more just it's just showing. It just shows that yeah, you don't have much experience writing it,
Yep.
uh, and that you need some repetitions, because once you get the repetitions, DFS and BFS should almost be, you should be like pumping out that boilerplate pretty fast.
Hmm. Gotcha.
So basically it just showed that you had to think about it a lot. So like where
Hmm.
do I do my visited? It should be boilerplate. Like just have this said visited there, and then everything else should be pretty similar. Pop left.
Hmm.
So here your path was append up here instead of at the
Yeah.
bottom. Then you're doing for edge, but we're actually visiting nodes. Visit that. Yeah, see, you see how they're both different. Sometimes, like when it comes to just coding in general, a lot of times you would want the functions to be written in a consistent way also for readability.
Yeah. Yeah, I definitely yeah, I never realized how the iterative DFS looks pretty much like the BFS. Um, so that's definitely a great learning point for me.
Yeah,
Not crazy.
yeah, and then yeah, my last thing would just be just managing the visited array, knowing
Mhm.
when to add it and use it. But yeah, I think overall you were able to solve it. Definitely study up on Dijkstra's. Maybe next interview I'll ask you something related to Dijkstra's. We'll see.
Okay. Okay,
But
I'll be sure to prep for that
but
then.
Dijkstra's is pretty common.
Uh-huh.
But honestly, they might only ask you that in Google. But it's
Okay.
pretty common. You might actually end up seeing it. I got asked it in a few interviews before.
That sucks.
Yeah,
Okay.
but it's pretty.
I'll definitely study.
Honestly, it's boilerplate DFS. Instead of using a stack here, you just do a heap here. It's pretty much
Uh-huh.
boilerplate. So you should understand the boilerplate of DFS and be able to change it up to a BFS, change it up to a Dijkstra. It's pretty easy. It's basically the same as BFS, but with a here you're gonna be using your heap instead, and then there's
Hmm.
gonna be slight changes, but it's gonna be pretty much boilerplate to this, honestly.
Okay.
Yeah.
Cool.
Cool. All right.
All right.
Well,
Thank you so much.
yeah, no problem. Do you have another one scheduled soon, right, or no?
No,
Okay. Yeah.
I don't.
Yeah. Feel free
I
if you want to
can.
keep scheduling, do
Oh
more.
yeah,
Just get
I'm
you ready.
definitely gonna keep scheduling.